Parsing and understanding documents for RAG is really hard, but when your documents look like this and this and this, it's next level ridiculous. But there's a way to get it done. I'm going to show you how we turn these three really difficult diagrams into something LLMs can understand, and you can get accurate RAG search out of it. Check it out. Hi, I'm Neil.
And I'm Daniel.
And welcome once again to RAG Masters, the world's only show about retrieval augmented generation. Daniel, how are you?
I'm doing great. There can only be one, Neil.
Yeah, I don't know if there's one because it's a terrible idea to do a show about it, but that could be the case. But here we are.
I'm having fun.
And too. And today we're going to talk about one of our favorite topics, understanding complex documents and turning them into LLM-ready data, and then ultimately downstream into accurate RAG search and being able to build applications around them. And I kind of love doing these demonstrations because people give us really hard documents. I mean, people don't let it, our customers and the people that use our platform, the developers, they don't take it easy on us. And so here's I collected three of the real doozies that we actually turned into really good data. This is some complex diagram of a flex-safe Palletank. I'm going to show you how we can do something with that. This is NASA has a giant computer rack. We'll show you what we can do with that. And then you're going to take us home on this explanation of mechanical engineering and soil substrates. Again, difficult material. And I want to show you how we can get it done. You ready?
Yeah. Yeah.
I'm ready. I'm sitting here. I'm ready. Let's do this already. Stop talking. All right. So let's start with this one. I want to take you guys into our application. This is so Daniel and I both work at iLevel.ai. We have a RAG platform called GroundX, which is like a full end-to-end RAG platform. And one of the things that's special about it is we trained a vision model on nearly 1 million pages of documents, some of them looking like this, but this was not one of the training docs, to be clear. And it allows us to turn them into LLM-ready data, identify the objects on page, chunk, parse, etc., and get you something useful on the far side for RAG. This tool you're looking at, we call it an X-ray, which is a way that we visualize what our vision model is doing on the page. And so in this case, the vision model essentially, now we'll say it didn't do perfectly, okay? And we'll be frank about places where we're not perfect. The vision model here identified this. This is the yellow box that the vision model is doing. So it nailed this entire complex part of the diagram and the legend, but it missed this little piece here. So I can't ask a question about that. But if I click on this, you'll see here we recognize it's a figure. This is all generated automatically, by the way. We generate keywords that improve RAG search. We create a summary automatically of this document, which improves LLM completion because it's describing contextually where this chunk is going to come from and what it's about. And then for every object or chunk, we create a narrative text, which explains this conceptually. And then JSON, which is the richer, fuller data of what this is actually about. So if you just take a quick look at this visual, I'm going to click here. The narrative text that describes it. The diagram illustrates the assembly of the flex-safe Palletank 500L. It includes a legend explaining symbols such as cable tie for securing components, a red X for sealing or disconnector points. Yes, and a green circle for the pump. Totally right. Look up here. Yep, cable tie, 2 cable ties, X for the sealer, and that thing for the pump. Component 1 is at the start of the flow, connecting to a sealing point 14, and on and on and on. I don't have to want to get too into the details of it. What I do want to ask, and actually I was wrong, it did nail this one, even though it's not quite in the drawn in the box. At any rate, let's ask a question, see if we get the answer right, and then Daniel, I want you to jump in and explain, how this gets done actually under the hood. So I prepared some questions here. Let's see. Where's the flex safe on the Palletank? All right. You could also ask, this is a folder that has, I don't know, a couple hundred documents in it, tough ones that we like to test on. This is the backend tool. We can do an eval chat really simply. Where's the ceiling cut on the, what's it called? FlexSafe tank. Now the ceiling cut was the X. Okay, in the FlexSafe tank, the ceiling cut points are indicated by the symbol X in the assembly diagram. Specifically, the ceiling mechanism is associated with elements at component 14. Let's go back here. Here it is, component 14. All right, Daniel, what is going on here? How is this possible?
Yeah. So, I mean, first of all, it's not your like normal RAG system, right? Like if you go on Medium and you read a blog post, or you go on like some normal RAG website, maybe it's like LangChain or like Llama Index or something, you'll get this classic chain, which is great. You chunk your document, you break it into little parts, based on the text, then you pass those to in vector encoding, and then you search via semantic similarity with your query. That's all well and good, except when you have something like this, right? So when you have these like crazy visual relationships between things, these types of documents are the types of things most people don't consider when they're building a RAG system, and they're the types of things that's going to like implode your RAG system. So how do we do it? What we do is it's kind of a two-part step. So first, we apply a detection model. It's called a detection model, where we're drawing these boxes. So we find specific subcomponents in the page that we would like to extract. And that's really important, because the next thing we do is we pass to a fine-tuned VLM. So we fine-tuned a VLM, a visual language model, that can look at something and then turn it into text that a language model can understand. So for this particular thing, we might turn to JSON, such that we can encode these sort of relationships between parts as JSON text. And that's well and good. That's really great. But we're still dealing with a VLM, and VLMs have some kind of constraints. When you give them too much information, they can lose stuff. And that's why detection is so important. We really kind of trim down what the model is really looking at and describing, so that we can turn into JSON. That JSON can then get passed to a language model so that it can answer your question.
And the key difficulty, really, the trick of this one is you have to understand a couple of things simultaneously. You have to understand this diagram. You have to understand this X, where it is on the diagram. And then you have to go to the key to understand what the X does. It's a ceiling, it does ceiling and cutting. So this is actually like a multi-step tango to answer this question. It's why I actually like this document, because it's pretty difficult to nail this one.
Yeah, and to piggyback on that a little bit, I think you're hitting the nail on the head. There are a lot of VLMs out there. You could pass this to like OpenAI, whatever, stick this in ChatGPT. You might get a good response. But if you're trying to do RAG at scale, getting those really good descriptions with a model that's economical to actually run on a large set of documents is really hard, which is why we went through the effort of fine-tuning one ourselves, so we can get those high-quality textual representations.
Amen. All right, let's go to the next one. This one's pretty cool. This is let me stretch this out. Let's get rid of this one so it doesn't get in our way. This is a page from NASA, from some architecture called IMPALA, basically like a rack in their data center. And there's obviously just a lot of density to this. It's kind of a nightmare to the density itself. But the thing I want to show you now is the relationship between ideas. In a way, it's similar to the one we just saw, but I think even tougher or a little bit different. So I'm going to ask a question about master node 1. And the question I'm going to ask, if you draw a line here, this is master node 1 right here. If you draw a line, which it has here, and there's another line over here which goes to this information that's also about this master node, the input power and the air temperature. So I've got a question teed up just to make our lives faster here. And here's what the answer should be. Let's see if we can get there. Okay, so let's go back to our system. All right, we're going to go here. This is where we have the X-ray, and just to show that this is authentic, we've captured this entire graphic as one idea. And, in here is the rich JSON, which explains where essentially every one of these objects are in the relationships. Let's ask a question, see if we nail it, okay? So go back up here, our eval chat. And I'm asking in the NASA IMPALA doc, what's the input power and air temperature rise, just so you see it, for master node 1? And just to keep this simple, I just say just the numbers, okay? Give us a couple of seconds. Input power, 368 watts. Air temperature rise, 241. Yep, 368 watts, 24.1. And we kind of nailed it. This one's tough too. And just to go back to it, master node 1 is here. Information here is 368 watts and 24.1. So Daniel, again, what's the magic trick here? How is this done and why is this hard?
Yeah, so I think it's kind of the same general sauce, right? We do a detection thing and then we turn it into JSON, and then that allows us to represent these complex relationships. I actually just had a conversation on Reddit like really recently about importance of graphs, and someone mentioned graphs are really important because that's what JSON fundamentally is. So for those of you who don't know what a graph is when you have a relationship or an entity and another entity in a relationship. So you can encode, like, think social networks, think things like this, where you have a description and then an item and then a description. I don't see a lot of parsers encoding information as JSON, but I think this really speaks to the power of JSON as a modality. Like thinking of it as like not just text, but JSON as kind of its own thing, because JSON allows you to have these hierarchical structures that allow things to relate with one another that is interpretable by language models. So you get the portability of text, but you get also the understandability of JSON. Language models are really good at understanding JSON. So you get the portability and understandability of JSON, but you get the rich structural capabilities that you might expect from maybe more visual modalities. So like this sort of intermediary JSON is really powerful, especially for this type of application.
Great point. All right, let's go to the last one. I'm gonna bring this document up. This is more of your background here prior to AI, so we can get into the engineering aspect.
Before I went to the dark side, my mechanical engineering degree.
But I brought this one up because I think it's like a chunking masterpiece. And one of the things that's kind of fundamentally different about our approach is we use this vision model as the chunker. So the first thing we're doing is the vision model, which we fine tune, is detecting all the objects on page, which eventually becomes the chunking strategy. Except when you have like a giant, if you have multiple pages of text, then we do more of a semantic strategy on those text blocks. When you have complex pages like this, like how do you chunk them? Well, the vision model in our case, and Daniel's going to explain this more detail in a second, is the tip of the spear for us, which is I think a really different fundamental approach than most are taking on how to do this. And so let's just jump in and let's examine this one. And just to be clear, each one of these colored boxes is a different chunk on this page, okay? If we jump in here, why don't you maybe just explain what we're looking at, and then we'll fire a question at it. And just so you know, it turns it into this kind of narrative text, which explains it pretty well. But this is going to come out in the question answer. Daniel, give us like the 30 seconds on what we're looking at, and then we'll fire a question.
Yeah, so this whole document is basically about a bunch of different load systems on Earth or dirt or whatever. Basically, if you have like a big building and you stick it on a thing of dirt, the dirt can only hold so much before it starts to do weird stuff like move away and spew out or squeeze out like putty. So you have to distribute your loads. And this image in the middle, I think, is the one we're going to be discussing. Obviously, we're processing all this stuff, but we want to keep it focused. This one in the middle is when you have a load, you can distribute that load over some surface area. And the expression is, the pressure is the force divided by the area, which is the A times B.
Right here. The bearing pressure is axial load over A times B.
Yeah.
And so this diagram is showing this axial load pushing down. There's some surface, there's bearing pressure. Here's A times B, and that distributes the load. Okay, so again, we prepped a question here. Maybe I didn't. I think the question was describe figure 1.26.
Yeah, I think so.
Okay. Let's go back and do a chat. Let's ask it to explain figure 1.26. Drum roll, please. And we get, this nice, pretty rich explanation, actually. But the nice part, figure 1.26, titled Axial Loaded Spreaded Footing, illustrates the distribution of axial loads across the spread footing. The diagram emphasizes how these loads are uniformly distributed, as Daniel said, with the bearing pressure calculated as axial load divided by A times B, which is exactly what we have here. Bearing pressure defined as axial load over A times B. So this is doing a lot of work to understand what's going on. Why don't you take us, into the AI side of this, move us away from the engineering side, the soil engineering.
Yeah, so if you can pull up the X-ray, I think it'd be particularly useful in this sort of circumstance.
Yeah, good.
So, there's a lot going on. If you asked a normal RAG system, what is it, figure 1.6 or whatever it was? Was it 1.6? Yeah.
1.6.
If you asked it what figure 1.6 was, it would probably get the answer right, because you have the text of the figure name right above 1.6. So if you had a naive system that was sort of scanning through the text and extracting this sort of information out, this thing that seems like a title is right next to 1.6. So you can answer that purely textually. What you couldn't do under any circumstance is know what the formula is with a system like that, because the formula is not text. The formula is in an image. So we have an image that has this formula that's getting described in a textual representation. And then this is kind of really important. We contextualize all of these chunks. So previously I said it's really important to keep things focused, right? Because we have a VLM that's trying to describe something textually. It's really important. If we have too much stuff, if you show this whole thing to a VLM, we'd probably miss something really important. So we break it down into really tiny chunks. The issue with breaking things to really tiny chunks, though, is you lose context. You don't know that this chunk is near this thing or that thing, which might be relevant. So one of the things we do is, after we break it down and then describe as a VLM, we then co-contextualize these things that are near each other. So the textual representation of the diagram has an opportunity to interact with the text that is the diagram and the diagram number. So that's how the language model can know that formula is kind of the essential idea of figure 1.6 when you ask it from a language model, because that information has had an opportunity to kind of co-contextualize with itself within our ingest process.
And importantly, you can do all of this in your own data center. You can do it with GroundX on premises in your managed cloud, or literally your data center, or even an air-gapped data center. So the platform is designed to run where your data lives. You don't have to go out to OpenAI. You don't have to go out to AWS if you don't want to. Of course, you can run it there if you like to. But this whole platform is really designed for secure RAG applications to live where your data lives. And look, that's it for this one. This is some of our favorites. These are really hard. We'll have more of these coming soon. And for folks out there, if you've got some wild documents and you're trying to build RAG around them, bring them our way. We'd love to see what you got and put us to the test. If you go to ilevel.ai, upload them for free, get your X-ray, you'd get something just like this. Click around in the JSON and put us to the test and let us know how we do. We always love a great challenge. We're not 100% perfect on everything. Nothing is, but we're trying to really push the limits of what's possible. And with that, that is this episode of RAG Masters. Daniel, what's your final word, my friend?
Like, comment, and subscribe.
My daughter just tells me I'm the worst at this, and she's probably right. Anyway, Thanks a lot for joining us. We'll see you on the next RAG Masters.